Hello, everyone. Welcome to the investigation of thermal conductivity of materials. My name is Christian Gonzalez. I'm a junior and I major in computer engineering.
My name is Daniel Ben-Hur. I am a senior and my major is petroleum engineering.
My name is Ryan Hernandez. I'm a sophomore and my major is pre-health and nursing.
Our 3-week investigation of the heat conductivity of solid materials, or how well a material can transfer heat, starts with the instruments and materials being used. For the experiment, the instrument we used was the TSL-100. It is a precise machine that is used to measure a solid material's heat conductivity. It can determine a material's heat conductivity directly using a detachable needle probe. The machine uses a 100mm probe for soft materials and 50mm probe for hard materials, such as concrete. The probes can produce heat and are a sensor to measure the heat conductivity of a material. The probe heats the material being tested directly, then allows the material to cool. While the material is cooling, the heat conductivity of the material is measured through the probe. For our experiment, we used a 100mm probe to test, heat, and measure 2 soil samples stored in pots with varying percentages of water being added to them. The machine we used for the second experiment was the Lady 40. This instrument measures the heat conductivity of materials indirectly through 2 different apparatuses. The main apparatus can measure temperature, voltage, and current. For our experiment, though only temperature needed to be measured, this machine has 2 temperature sensors that measure the temperature in Celsius for each of the 2 plates on the second apparatus. The machine has a built-in timer to be used when taking data. The timer can be set to tenths of a second, hundredths of a second, or thousandths of a second. The secondary apparatus has 2 plates along with a fan. The fan is used when recording the temperature when the cold plate is cooling. The main apparatus was used in measuring the temperature of the 2 plates. To control the temperature of the 2 plates, there is a manual knob and a proportional integral and differential system, or PID system. The PID system changes the temperature of the plates to stabilize the temperature between them. The system heats the plate above and cools the plate below without having to use the manual temperature knob to stabilize the 2. We used the PID system to ensure we had a consistent starting temperature for all trials of each material. We measured the heat conductivity of 3 materials using the Lady 40. Plastic, wood, and rubber. To measure the heat conductivity of these materials with this device, calculations are done by hand after data has been recorded and the material is cut into a circle the same size as the 2 plates. To measure a material, the material is placed between the 2 plates and is then pressed. In this manner, we use the formula of the constant rate of flow of heat through the material to calculate the thermal conductivity of each material. To get accurate measurements of the materials themselves, we used a triple beam balance scale to weigh the materials and calipers to measure the dimensions of the materials. Our goal was to learn how to use the TSL-100 and Lady 40 to determine the heat conductivity of different materials, so we can infer how the heat conductivity would affect the materials and analyze how it can affect what a material could be used for.
To begin our experiments, we began by using the TLS-100, which tested the thermal conductivity of soil with different levels of hydration inside the soil. It was by far the most time-consuming due to the fact that it's mostly automated testing. To begin, choose the 100mm needle probe and make sure at least 100 centimeters of height of soil is inside the container, and write down the weight of the soil sample to ensure the correct amount of hydration is added later in the experiment. Turn on the TLS-100 and configure all the settings. For our test example, we used a mode called auto testing, which allowed us to set up an amount of trials and amount of time in between each trials, which was 6 trials per sample and at least 15-minute intervals in between each trial. Before testing the soil, we must stabilize the temperature or else the readings will not be accurate, which took no less than 15 minutes to stabilize. Once everything is ready, we can begin using the TLS-100. Each test is roughly 5 minutes in duration, and there is a minimum of 15-minute break after each test as set up previously in the auto testing, which is why testing took so long to complete, because the majority of the testing was done automatically, whereas later we discussed the Lady 40 was much more manual work. We ran each hydration level 6 times, and we added 15% by water by mass, all the way up to 75% water inside the soil, which was a total of 6 trials done. After each level of hydration was added, we had to make sure to thoroughly mix the mixture of soil and the water in order to receive accurate readings from the TLS-100, or some of the soil would not be hydrated, throwing off the calculations in the end and overall causing a shift in our uncertainty analysis. After the first soil sample, we ran it all over again to maximize precision and accuracy, to observe its experimental uncertainty, and to show how reproducible our results were. After each test, we were given two values, the K value, which stood for thermal conductivity, and the R value, which stood for the insulating value. These two values were important to understanding how the water affected soil. The higher the K value, the better the thermal conductivity, the higher the R value, and the better the insulating factor, and that's because the R value and the K value are inversely proportional. We plotted all of our data in Excel, and we made two graphs from the data that was given from the TLS 100, as seen in figures 1 and 2 on our poster. These graphs showed the thermal conductivity as the level of water increased. We also plotted the experimental uncertainty using error bars in figures 1 and 2 by finding the standard deviation of each test. Both graphs were similar with each other, and based on our uncertainty analysis, we can conclude that these measurements is reasonably precise, therefore proving accuracy in our measurements using the TLS 100. Both of these tests that we ran led to the results of the two soil samples. In both experiments, thermal conductivity increased as the water percentage increased in the soil. However, the insulating factor decreased as we added more and more water because the more heat could escape now that the soil was hydrated. The resistivity of the sample is inversely proportional to thermal conductivity. Therefore, we can conclude that the more water you add to the sample of soil, the more conductive it is versus a sample of unhydrated soil.
Using the LEDI 40, it gave us the opportunity to measure heat conductivity because we were able to view how well heat had transferred through a specific material. The LEDI 40 could allow us to detect changes in temperature of our samples, such as plastic, wood, and rubber. The way the LEDI 40 works is the following. There's a hot plate on top of the instrument that is heated to a desired temperature. In our case, it was a constant temperature of 85 degrees Celsius. Below the hot plate was a cold plate sitting at room temperature with a thermometer inside, giving us the ability to detect the temperature within the cold plate. We prepared the sample in such a way that the sample can perfectly fit in between the heating and cooling plate. In other words, the diameter of the sample is exactly equal to the diameter of the heating and cooling plate. All of our recordings for heat transfer was done in Excel. Once our hot plate had reached 85 degrees Celsius, we can sandwich our sample material and record the change in temperature of the hot plate and cold plate. We chose to record the temperature every 15 seconds and did this continuously until the hot and cold plates both reached a stabilized temperature. Each trial took at least 45 minutes. That includes the heating and cooling portion. We repeated the experiment for each sample at least 5 trials to reach the stabilized temperature. We slightly heated the cooling plate and allowed it to cool freely at room temperature, and we obtained the cooling curve. We obtained the cooling curve for every trial. We draw the tangent at the stabilized temperature of the cooling plate. The slope of the tangent provides us a rate of cooling at that temperature. It was manual work that required patience and persistence, recording the cold plate's temperature every 15 seconds for each trial. We found that the measure of thermal conductivity was low, which indicated that materials like wood, plastic, and rubber are poor conductors of heat. We also calculated the experimental uncertainty for each sample and found that our experimental uncertainty was reasonably low. This clearly means that the LEDI 40 is a very precise machine to measure thermal conductivity of solid material. These experiments have taught us how to view the measurement of heat conductivity and electric conductivity in a new way that can help us learn in the future. We want to thank you for listening to our poster presentation on the investigation of thermal conductive materials.